on this computer. All right, we are recording it now, so that everybody knows. All right, so questions?
I have a quick question. Are you going to be posting next week's schedule soon?
Yes, probably today. Actually, I should. I usually post that on Thursday. I thought to do it even more ahead of time, but I'm just finishing it last minute. So, but I will post the schedule today. So by today before midnight, you will see the schedule posted as next week. I usually like this week and next week, you know, so it will be next week, and then on Sunday I'll switch it, and that will become this week. So it will be posted.
Thank you.
Welcome. Are there any other questions? Also, what you can look for today, I graded most of the things. The only thing I didn't grade is quiz 4 that was due yesterday, and I plan to do it also this afternoon. So just check for your grade will appear in a couple of hours. So that's kind of timing wise. So how does the chapter look like? Is it much harder than in Calc 1 integration, or it's more or less similar, or what do you find kind of most complicated? No particular objections? Parmida? I agree. That's how this chapter has a flavor of like a cookbook. You know, if you see this, do this. So it's less general principle. These are more specific kind of strategies, and you need to memorize them. Like in A3, like if you see sine, cosine, do this. If you see tan, secant, do it. And you have to memorize it. Otherwise, you're not going to do well. You know, so you have to memorize all these cases. Or are you going to do secant substitution, or sine substitution, or tan substitution? So generally, all those should be memorized.
Is there any?
No. Someone asked me that, and I posted that information. Are there any other questions?
I have other questions if no one else has questions.
Please go ahead.
Okay, so on the same practice test, on number 5, could you attempt doing that with converting it to sine and cosine instead of tan and secant? Because
sometimes that's doable, sometimes that's complicated. But
but so in the book, it says that if it's a tangent and it's to an odd power, that you can attempt to do it with sine and cosine, and that's what I did, and I got an answer.
No,
but
that's not good. I don't know why are they conflicting their own strategies. So strategy, so if you see tan and secant, as I said, if you see tan on odd or secant on even, we have very good strategies. Because problem when you write sine over cosine, the trouble is that very often you end up with a 8-5 rational function with high powers and a very unpleasant one. But doesn't matter. Let me
it's just tan to the 5th of x over 3 dx.
Here is one thing that I never really showed on the screen or in the notes, but I'm tempted to do it. I don't like to work with this x over 3 all the time. So generally, that's inexpensive substitution and saves me from writing. So let's generally what? Let me do, as I said, doesn't help you at all. So u equals x over 3. So du is 1/3 dx. So dx is 3 du. You understand what I'm doing here? Just dealing with the fact that they asked me to do x over 3. So now it will be 10, 5 u du, and there will be 3. This is much cleaner because I paid a little price in the beginning instead of paying it all the time to keep in mind a linear correction, this and that. I think this is cleaner, right? You don't have to do it, but I think it's a good idea. Sine 5u over cos. And then exactly as you mentioned, since I have odd number of signs, then we'll do the following: sine 4u. Actually, this will not be bad at all. I was too critical. So what do we do here? Since I have derivative ready and even power, no, sign. So since I had odd power, I separated even and one extra. One extra is for derivative ready. So I get the V equals what? Cosine U. So dV is negative sine U. So this is negative dV basically. So I get negative dV integral. So E. The good news is that our denominator is actually compact. It's not V plus or just a V itself. And then what? Sine to the fourth U. So I'll say what? Sine square U is 1 minus cosine square U. 1 minus squared. So then sine to the fourth U is just 1 minus V squared. And then what do? I just square for this 1 minus 2 squared plus U to the fourth. Are you following my work? Nikki, is this okay?
Got it.
Okay. And then what do? I just split it and finish table integral. So this will be integral of 1 over V to the fifth dV minus integral 2 over V cubed dV, because V squared and V fifth cancel each other out, plus integral of 1 over V, which is what? Negative 3 times. This is V to the negative 4 over negative 4, negative 1 quarter V to the fourth. Plus 1 over V squared, because it's V to the minus 2 over negative 2, and negative 2 and negative 2 cancel each other out, plus ln V plus C. And that's it. So then we recall that V stands for cosine U, so it will be 3 over 4 cosine to the fourth, and then U will replace with x third.
Could you move the camera down, please?
I better write up. So can I continue here?
Yeah.
So it's 3 quarters times 1 over V to the fourth, which is 1 over cosine to the fourth of U, which is x over 3, so I'll return that back. Minus 3 times 1 over cosine squared x over 3, and minus 3 delta of cosine x over 3. I can squeeze it in so
Cool. So I got the same answer, and then I compared the graphs of this answer and the answer you have on the answer key, and they aren't the same graph, so I was a little confused.
Probably you entered it wrongly in the calculator, you know.
Oh, but then I checked on wolframalpha.com, you know, so like you can see like what you entered properly.
Okay, I will double check that solution, and then I'll put them both in calculator and compare if there is some error there.
Yeah, because I got the exact same one as you did.
There are many things that can happen with that graphing. It might be that I made some error, or it might be also that you entered wrongly. Maybe you put parentheses. That's what happened last time when we did review. Someone didn't enter correctly in calculator, and the other thing is sometimes graphs differ by 1 or 2 because of that plus C. So it might be that they look like this. But as I said, I'll just check both, and then let me take a photo of this one. So do I have it? Yeah, so let me take a photo so that I can. Although I have it extra. I have the other one that I posted, and I'll compare it, and if there, and I'll post.
What goes on the part where you switch the sines and cosines for V's?
What do you say?
Could I ask again? Could I ask what's going on in the part where you switch the sines and the cosines for V's? I can't quite follow with the operation right there.
Where? Here? Up or down?
Yeah, I guess. In between there on the line where it says 1 minus 2V plus.
So sine tan U is written as sine over cosine. So I have 5 sines on top and 5 cosines on the bottom. Do you see that?
Okay, yeah.
And then what? Among those 5 sines, and that's the strategy when you have odd power on top, Among those 5, I kept 4 here and I put 1 on the side next to du. You see,
Okay.
those 5 were split into 4 and 1. And that's why odd is good. Because odd is good because I can give a 1 for derivative ready and have even leftover. That even leftover is very important. Why? Because here is what happened here. If you look at that sine u du, that's derivative of cosine u with a minus. So that tells me, oh, a good substitution is to put the v to be cosine u. Why is that good substitution? Because it's derivative ready. dv is negative sine u du, and that's exactly this package here with an extra minus that I put in front. Does this make sense?
Yes, thank you.
And then what? Then denominator is cosine to the 5th, and that's exactly my v to the 5th. But the best thing is, since sine to the 4th was even power, here's what I could have done, what I was able to do. So sine squared plus cosine squared is 1. So basically, I don't know if this makes sense. So I know that sine squared of u plus cosine squared of u is 1. But cosine u is v. So I have sine squared u plus v squared is 1. So sine squared u is 1 minus v squared. And then, but I had sine to the 4th, then I just squared both sides to get that 4th power is this. So that's what I fed in there, and I foiled it, and then everything went fine. As I said, if my leftover was odd, then I would need some radicals and things would be just completely stuck. So that's huge difference.
Okay, thanks.
Feel free to ask me again for a certain passage. So if it doesn't make sense, just go ahead. I'll go forward through a certain line.
I have another question if no one has questions.
Go ahead.
All right, so on your first practice test for summer 2012, for 9B, I understand your solution until like step 3, but then I don't understand how you switch the bounds of the integral. It was originally from 0 to a, and then you switched it from a to 0.
Yes, I always do that when there is a minus. So that's a property of integrals. When you flip the limits, minus is either produced or spent. And usually when I have a minus, instead of putting minus and parentheses, I just flip the limits, and that basically does quick way to distribute. So it must be that there was a minus. So
Oh, okay.
And that's
Okay.
just helps you. If you don't like it, you don't have to do it.
Okay. Yeah, and the result actually is negative infinity minus 0. So what would that be?
So that would be negative infinity.
Okay.
So that means.
Oh, sorry, negative infinity times 0.
Oh, that one you cannot decide. So.
Oh, okay.
People very often misunderstand that. You know, sometimes our language is really not precise. So when I say this, you know, then very often people make the following conclusion. Anything times 0 is 0, so this is 0. That's not true. This is really not 0. What this really stands for is a negative big number times a small number. So that's what this 0 stands for. Something that approaches 0, something that's small. And big times small could go anyway. That's why we say that that's indeterminate form, because depends who is pushing stronger, big to be big or small to be small. So those two are not balanced. So that's fine. Just a second, someone wants to come in. I'm doing some online office. Sorry, to bring. Yes. I will be down in like. Okay. Sorry, there was some organization. So go ahead.
What?
Are there any questions?
I mean, I still have questions. If no one else has questions, all right.
If one person has questions, probably the others are benefiting. That's why they came, to just hear someone else asking, and then making their own conclusions. So what's yours?
So for a couple of questions on the practice test, there are like harder things to factor. So like it goes, so like one of them was like x cubed plus minus x squared plus x minus 1. And then the solution for that was to factor it into x squared plus 1 x minus 1. So I was wondering how like you attempt to factor those things.
So what was the one x cubed? What?
It was just x cubed minus x squared plus x minus 1. And when I originally saw that, I didn't know that we were supposed to attempt to factor it.
Yes, so generally one of the main lines in this section is that every real polynomial could be factored into product of linears or quadratics. So I don't want to see a cube. So I just want linears and quadratics that cannot be factored out. So when that happens, what do? I have two options. One is if I developed enough factoring skills in pre-calculus, then I can factor it. If not, then I can use graphing calculus. So I'll show you both. So here it is. If this is P of X, I would say that it's quite obvious that we can group them into pairs. Do you see that?
Yeah.
So what happens on the first couple? I can factor out x squared. Do you see that?
Yeah.
On the second couple, I have 1 times x minus 1. Can I factor out something?
The x minus 1.
And that's it.
Oh, I see.
And I thought that was very straightforward.
Yeah, okay.
What happens if you don't see this, or if I assign problem that's even harder to factor out? Here's what you can do. In pre-calculus, you learn something called factoring here. So what you do is the following. Try to plug in the numbers just by luck to make this a 0. So guess zeros of P of X. Basically, you don't even need to guess it. You know what you can do? You can put it in graphing calculator and look for zeros, and you will see them on the graph. Do you agree with that?
Yeah.
So one way or the other, it's very easy to see that P of 1 is 0. So when I plug in 1, I get 1 cubed minus 1 squared plus 1 minus 1 is 0. Is that okay?
Yeah.
So what is that telling you? If P of 1 is 0, there is a theorem from pre-calculus called factoring theorem that guarantees that you must have a factor x minus 1. If it was P of 3, it would be x minus 3. So generally, what's missing here? What's missing is what is that other factor? Do you agree?
Yeah.
So how do you get that other factor? You can kind of work backwards and see what it should be. What should it start with? Although I'll show you a better method, but this one also works for easy examples. What should it start for? Because this product will give you x to the cube. So starting number must be what?
X squared.
And then this negative 1 and something should give you this last one. So what should that be? Plus 1.
Yeah.
Do you agree?
Yeah.
So the only thing that we didn't conclude quickly is the middle term. And then here's what I do. Look, if I FOIL here, let's say it's AX. I don't know what A should be, so I'm guessing what it happens. Look what it says here. X times 1. You see that? When you FOIL. That gives you X. Do you agree?
Yeah.
And gives you minus AX. It should be how much? X. So Johnny says, oh, I don't need anything because it's perfect the way it is. X times 1 is X. Here it is. Everything is good. If you don't like this guessing, here's what you can do. When I got this x minus 1, the second factor, you can just divide it. So you divide x cubed minus x squared plus x minus 1 by x minus 1, and then you see what you get. X into x cubed goes x squared, x cubed minus x squared, and you subtract, there's nothing. X minus 1 into x minus 1 goes 1, here's plus 1. And here is that quotient. So I'm telling you, this was really easy to factor, but these are strategies if things get a little more complicated. And one more thing, if you don't like this division, this one could be done using so-called synthetic division. Review synthetic division. Synthetic division. These are in my lecture. So how do you do synthetic division? If it's x minus 1, you put 1 here, and you put coefficients of your polynomial here. 1 minus 1. I copied all the coefficients. If one coefficient is missing, you must put 0. So here it is. 1 goes down. 1 times 1 is 1. I put it here. When I take 0, 1 times 0 is 1 is 1. This is a remainder, and we are not surprised that it's divisible. So what is this? 1, 0, x, 1x squared. Here it is, quick division. So there are many ways to do the factoring. And as I said, if anything happens, you just put it in a calculator. When you get a couple of zeros, usually you will get an idea how it factors.
Right. I have a quick question from the last practice test. Question number 2, you were given y equals and then an x value, but you in the answer key you change it to y opposed to x. Is that just to make it easier, or is there a reason for that?
I don't know. I'm sorry. So can you read it to me, and then we'll do it, and then because if I start to find it, then we'll spend lots of time. So go ahead. What was the problem?
It says find the area of a region bounded by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. And in the answer key, you change it to y plus 1 and y squared minus 6 over 2. So I just wanted to know what the reasoning was behind that.
Oh, yes. That one was actually a little tricky problem. Probably that year we emphasized this a little more. I mentioned this, but I don't know if in my lecture notes I showed you enough. Here's what's happening. Y equals x minus 1 is a straight line. Okay. Y squared equals 2x plus 6, that's actually upside down parabola. So, and that one has a 0 at negative 3, and it looks like this. So this is the area that I'm asking about. And what happens? We said when you need to find that area, whatever you do, you need intersection points. So I need to get a limit. So I need this point, and they are intersection points. So what do? I set them equal to each other. So when I plug in x minus 1 for y, I get x minus 1 squared. Then I FOIL, I get x squared minus 4x minus equals to 0. X minus 5 times x plus 1. So that will tell me that x equals 5 or x equals 4. So 5 is here. That's 1. It has coordinates 5 and 4 because y is x minus 1. And this point B is what? Negative 1 and negative. So here it is. I found the intersection. I have information about the region. And I have two options. I can treat it vertically. So when I say vertically, that means y is function of x. If I treat it horizontally, then x is a function of y. And I decided to treat it horizontally. It's up to you. Why? Because if I were to use it vertically, then here's what happens. By the way, what is this one? If I treat it vertically, then between negative 3 and 0, I would have one wing of parabola down, one wing of parabola up. Then between 0 and 5, I would need to split it and then get the area between line and parabola. It's a very complicated to set up. So that's the reason why instead of looking at it this way, I actually looked at it this way. So just switch the role of x and y, and everything becomes much cleaner. So that is the reason. This region really behaves much better if you think horizontally. Why? Because just now you use y-axis. Here are the borders. Here is the upper end of the stripe. Here is the lower. So So what did I do there? I said the following: area equals the integral will be dy. So I'm taking x as a function of y. Y is my variable. Lowest limit is -2. Highest limit is 4. So these are limits for y. -2 to 4. And then instead of looking up minus down, I'm looking right minus left. All the time, wherever you are. Actually, who's your right? Right is the line, left is parabola. So nothing to split, just, so my line, but line must be x as a function of y. So from here, I solve x equals y plus 1. So, so it's what? Y plus 1, that's the right one. Minus, your left one is parabola, so I need to solve for x, which is y squared minus 6 over 2. Right, that's it. This will be easy integral. Once you set it up, easy calculation. So the reason why we switched x as a function of y is because the setup is much nicer this way than this way. This is one of the most typical examples about that difference in setup. And basically, it's also a good thing about it, this prepares us for some type of integrals in calculus 3, where we really very often do that change of perspective. It is a little harder, so definitely it must be, it was on ground class, so it must be that I emphasized a couple of problems like this to prepare them for this reason. But it's good that you asked for this one, because without seeing it, it would be hard to make this decision on your own. It could be done the other way, but it would be very unpleasant. It would need really lots of skills in the setup. Next question.
Can you look at 5, like how you approach number 5? Because I think the denominator was hard to split up. Like I didn't see that originally.
So number 5. What's number 5?
Just the integral of x over the square root of 3 minus 2x minus x squared.
All right. What would I do here? The main problem here is this, obviously, the square root here. Do you agree?
Yeah.
So I would first try mild strategy. So for example, do I have derivative ready? No, I don't, because I would need minus 2x minus 2 numbers missing. So generally, what is the safest thing? This looks like 1 minus x squared. So this is like arc sine substitution or something like that. Unfortunately, this x term is bothering me. And what do we do in this case? We complete the squares. That's the first thing. Well, complete the squares. So how do we do that? 3 minus 2x minus x squared. When I have a minus, when I complete the square, I pull it out, because otherwise it's hard to work with that. So everybody switch sign, I'll keep minus out. Then here you have 2x. You add 1 to complete the square, subtract 1, so I get minus. So then it's minus of x plus 1 squared minus 4. At the end, I have 4 minus x plus 1 squared. This looks much better. So at the end, I have the following integral of x over square root of 4 minus x plus 1 squared. So what is this? This is now sign substitution. So how do we do that? I can do x plus 1 equals u, but I will directly say x plus 1 equals 2 sine. Why 2? Because of that 4 here. So we said if you have a squared minus x squared, then x equals a sine t or sine u. And here's what happens. So we get dx is 2 cosine u du. Let's a discontinuation of the square. And things will start looking better. Integral still not too good. What do I replace for x? I think we need to do work in this box. I better prepare it nice. How much is x? No. X plus 1 is 2 sine u. Well, let me take care of the square root. So square root of 4 minus 4 sine square u, and that is 2 roots of 1 minus sine square u. 1 minus sine square is cosine squared. That's the whole how that strategy goes. So that's 2 cosine u. So on the bottom, we get 2 cosine u, which is good news. Root radical is gone. X, obviously, from here I subtract 1, so I'll get 2 sine u minus 1. And then dx is 2 cosine u. And that's beautiful because these two guys cancel each other out, and this integral is absolutely trivial now. So it worked really fine. So this would be what? Minus 2 cosine u minus u plus. And that's it. So what would that be? Minus 2, I'll leave this guy. How much is u from here? So it's arc sine of x, arc sine of x plus 1 over 2. I solved this. I divided by 2 and took arc sine plus c. What about this cosine u? I either use identities or just set up a triangle. Remember that. So how do we do that? U is here. And it says here sine u is x plus 1 over 2. So I put x plus 1 out here. I put 2 here. Then I do Pythagorean theorem. That would be square root of, well, doesn't matter. I can use what I already calculated. It would be 4 minus x squared minus 2x minus 1, which is exactly our starting expression. So how much is cosine u? It's this guy over 2, which would be square root of 3 minus 2x minus x squared over 2. I just read it from here. 4 minus 1 is 3. This over this is cosine. 2 and 2 cancel. Does this make sense?
Yeah.
So the biggest obstacle here is actually to complete the square. So whenever you see under the square root quadratic expression with the middle term, that means complete the squares, and then things open to our strategies nicely. All right, probably we have time for one more question because my class starts in 7 minutes. So one more question. Go ahead. Absolute value. So here it is. My suggestion is it's a little tricky to carry them when they're both positive and negative. Do positive case first and then adjust the result for negative ones. Because most often when we do the problems, we can just consider the positive ones and flip it. So generally, if you do the positive one, I would just give you the full credit. Because it's a little subtle to do that. It's not too hard, but I'm mostly concerned if you can get positive case. As I said, at the end, you just analyze when you switch a sign, what would happen with your answer? Would it be adequate the way it is, or you need switch sign, or you need absolute value? So that's fairly simple analysis. It's easier than carrying that ambiguity all the time through your calculation. That's really weak bias. All right, if there are no other questions, then let's wrap it up for today. So probably, well, from tomorrow, actually, people start taking the exam. If you have some questions, send me emails. And then we'll probably have our next review like Tuesday night, not in here, but online. So if people are interested in that. So I think that this will be our standard schedule. Thursday on campus and Tuesday in the evening online. Goodbye, everybody.
Bye, thank you.
Good luck on the exam if you take it in the meanwhile.